This is going to show how to tell if this zone valve is working correctly. Check the voltage. Right now the thermostat is not on for this. So we look at the number one terminal here, that's for the motor. Let me put the multimeter over here. So we can see the reading. Can we see the reading? Yep, 0. All right, doesn't show anything. I'm going to turn on the thermostat. Let's check the voltage now. Yep, there's voltage, 22.4 volts. So that's telling us that electricity is going there. At some point here, the valve will open up, and then we'll see 24 volts. All right, it just turned on. I'm going to check this now. Well, 25 volts. So that valve is working correctly.
Wow, here it comes.
I had an interest in the electrical power, and being that this program's real broad, it doesn't set you on for any one career path. There's a bunch of different paths you can take with it. I like the hands-on learning done on the simulator and throughout the labs, and also the trips that we've taken into the field. We went to a transmission line control room and hydroelectric power plant. It kind of exposes you to what you'd be doing and what is done on a day-to-day basis in the field.
The biggest subgroup of the graduates from this program end up working in electrical generating stations. The power plants need to be operated 24 hours a day, 7 days a week. There aren't a lot of younger people working in that field, so there's going to be a large amount of retirees in the next 5 years. We try to keep current with the trends and what's changing in the field to make sure that these students have the skills that are current.
I like the 2-year part of it. You weren't locked in for 4 years, but yet with a program like this, you can go on for 2 more years and get a bachelor's degree in engineering, so you can make the decision by yourself.
Because this is quite a big house and the panels are a long way from the inverter, a big part of the job, and quite a tricky part of the job, is actually stringing the cable from the panels to the inverter.
Okay, one of the things we've had to decide on is where our cables are coming out onto the roof. Just up in the top left-hand corner, I've moved a tile out of the way, and after discussing with the rest of the team, this is where we're going to do a penetration for my cables to come out. The reason I've picked that spot, it's higher in the roof, so if I've got to get inside the roof, I've possibly got more room in there to move around in, plus it's making it a shorter distance for our cable, which we try to keep the cables as short as we possibly can. Okay, what I've got here, I've got my 2 DC cables for my positive and my negative, plus I've got an earth cable that we bring up as well. What I'm doing at the moment is I'm going to start and run these in the roof. I've got a spot down along the side near the gutter in the eave, so I can use my conduit here to just slip it along and run my cable through that part. Once I get to the corner here, down the bottom here, I will have to get inside the customer's house through their manhole and run the rest of the cable around to our exit point underneath the panels. As you saw earlier, I've run the cables along the eaves on the outside in the roof there, but now I've got to go inside the roof, so I've got to bring the cable across and out for our penetration. I'm going to actually clip my cables down. I've got special clips that I clip it to the timbers inside the roof. Okay, so in I go. When we bring the cables up through the tile, we drill a hole in there. It's a 25mm hole we put in there, and then we pull the cables through it, but we put a sleeve over it of corrugated conduit, which is 25mm, so it's a fairly tight fit around it. But then we put a lot of silicone around and pat that down, and that actual penetration is actually done underneath the last panel. So one, it's got silicone around it, it's sealed off that way, and we've got a panel over the top of it. The chances of any water getting in there, really don't have any issues with that, with water getting inside the roof around that, as long as we do the silicone and have it
To fulfill their missions, modern Air Force installations require an adequate and reliable source of electric power. This electric power, through an intricate network of wiring installations, provides lighting and power for a variety of requirements. The maintenance of these wiring installations is important not only to provide for uninterrupted operation, but because of the fire and electric hazards that result from defective wiring and equipment. In almost any electrical system that is in use over a long period of time, some malfunction will appear. To prevent possible damage to equipment, unnecessary work, and loss of man-hours, analyzing and correcting the trouble must follow a planned, logical approach. A thorough knowledge of effective troubleshooting procedures will help you locate the trouble quickly, correct it, and restore the electric circuit to a safe condition. A comprehensive knowledge of troubleshooting techniques is valuable wherever electric power is in use. In wiring new construction, troubleshooting techniques are invaluable for checking out the circuits as they are installed, thus assuring safe, trouble-free service. Whenever repair work is necessary, the same techniques permit the electrician to quickly identify the circuits that require modification and allow him to proceed with confidence. And of course, in maintenance work, correct troubleshooting techniques are the key to rapid diagnosis of circuit problems. Trouble in an electrical system will generally be one of three types: short circuits, grounded circuits, or open circuits. One must be able to recognize the different types of trouble and identify each one. An electric circuit is a path or a group of interconnected paths capable of carrying electric currents. An electric circuit exists when a source of power is attached through a pair of conductors to an electrical device, such as a lamp. Current flows from the power source through the conductors to the electrical device. To provide a measure of control, a switch is normally added to turn the circuit off and on. To protect the circuit from damage in the event of trouble, a fuse or circuit breaker is added to the circuit. Let's take this basic circuit, enclose it properly in protective boxes and conduit, and use it to demonstrate the three most common types of circuit trouble. First, we'll examine a short circuit. A short circuit results when two bare conductors are permitted to come into contact with each other. The current no longer flows through the entire circuit. It is shunted directly from the hot conductor to the neutral conductor. When this occurs, there is only a very small amount of resistance in the circuit. According to Ohm's law, for a constant voltage, when the resistance is lowered, the flow of current goes up. This increase in current can cause heating of the wires and is the cause of many electrical fires. However, since the circuit is properly protected, the fuse or circuit breaker reacts to the excessive current and blows or trips, stopping the current flow. To correct the short, the damaged wires must be separated and, in most cases, replaced. Then, replacing the fuse or resetting the circuit breaker restores the circuit to normal operation. Now let's examine a grounded circuit. In any electrical installation, it is standard safety practice to connect the neutral conductor to the metallic structure of the power panel. In this way, the protective covering over the entire circuit, the conduit system, has the same potential as the neutral conductor. A grounded circuit results when the hot conductor is permitted to come into contact with some metallic part of the wiring system. Since the metallic parts of the wiring system are at ground potential, the current flow is shunted through the metallic structure to ground. Since the resistance of the circuit is lowered to an extremely low value, the current flow is increased until the protective device in the power panel reacts to stop the current flow. To correct this condition, it is necessary to locate the undesired grounding of the hot conductor and remove it. Then, when the protective device is reset or replaced, the circuit is restored to service. An open circuit results when one or more conductors in a circuit become broken, burned, or otherwise separated to interrupt their continuity. An open circuit prevents any flow of current in the circuit. In this example, the neutral conductor has been broken to stop the current flow. If the hot conductor was broken instead, the effect on the circuit would be the same. If any part of this circuit fails, it breaks the continuity and stops the flow of current. Replacing the defective circuit component or repairing the broken wire restores the circuit to normal operation. The fuse or circuit breaker normally does not react to an open circuit. In the field, electric circuits are generally installed in a manner that rules